Hello everyone. In this lesson, we will talk about the first chapter of low-frequency electronic circuits, the crystal diode. All students, hello. Starting with today's lecture, I'm going to talk to you about the first chapter of low-frequency electronic circuits, the crystal diode. First, let's make a brief introduction to diode devices. The diagram at the top left shows the various types of transistor diodes, as well as their shapes and packaging. Regardless of the type of diode, its main characteristic is to have a unidirectional conductivity. What is the unidirectional conductivity of a diode? Let's take a look at the schematic diagram of a diode structure. The inside of the right diode consists mainly of a p-n junction. It has a p-type impurity semiconductor region and an n-type impurity semiconductor region. These two areas are combined by a corresponding process to form a p-n junction. The electrode from the p-type region is called the positive electrode. The electrode from the n-type region is called the negative electrode. When the p-type area is connected to the positive pole of the external power supply, and the n-type area to the negative pole of the external power supply, there will be a positive current flowing through the p-n junction. But when the p-type area is connected to the negative pole and the n-type area to the positive pole, no current flows through the p-n junction, which is a cut-off state. Well, the p-n junction only allows current to flow in one direction, so we call it one-way conductivity. In a circuit, a diode is usually represented by the following circuit symbol. This side is a positive pole, this side is a negative pole. When the p-n junction is positively biased, the direction indicated by the arrow is the direction of the actual current. Next, we will introduce why crystal diodes have unidirectional conductivity. Before introducing its characteristics, we need to know some semiconductors' basic knowledge. Okay, now let's look at the fundamentals of semiconductor physics. Materials in nature can be divided into three types according to their ability to conduct electricity: conductors, insulators, and semiconductors. Conductors, as we have learned, are substances that conduct electricity easily, such as metals, and insulators. They are almost non-conductive materials, like rubber, ceramics, and so on. The conductivity of a semiconductor is between that of a conductor and an insulator, such as silicon, germanium, and biochemical potassium. Then, the other characteristics of semiconductors are that, under different conditions, such as different temperatures, different lighting, and different purity, their conductivity will vary greatly. Using these characteristics, we can make semiconductor devices for a variety of purposes. For example, as the temperature increases, the conductivity increases. We can make thermistors, and as the conductivity changes with the light intensity, we can use it to make photoresistors, phototubes, and so on. In addition, when impurities are added into pure semiconductors, the conductivity will increase dramatically. With this feature, we can make crystal diodes and triode and so on. Okay, let's learn some common things about semiconductors. Let's start with the first concept, the intrinsic semiconductor. The most abundant semiconductors in nature are silicon and germanium. These are their individual atoms, and they all have 4 valence electrons in their outermost layers. For the convenience of description, the nucleus and the inner electrons are described by an inertial nucleus, as positive 4 plus a circle in the right figure, which we use to describe the inertial nucleus plus the valence electrons in the outer layer. For valence electrons, this model is called the inertial nucleus model. We use this model to describe silicon and germanium atoms. Let's look at the covalent bond structure. In silicon and germanium crystals, the 4 atoms around one nucleus are held together by 4 covalent bonds. In the whole crystal, the internal lattice arrangement is exactly the same. We call it a single crystal. So the single crystals of silicon and germanium are intrinsic semiconductors, or pure semiconductors. The second concept that we want to understand is intrinsic excitation and recombination. For pure semiconductors, when the outside world is absolutely zero or there is no light and so on, the valence electrons are completely bound by covalent bonds. There are no free moving charged particles in the intrinsic semiconductor, so it can't conduct electricity. which is equivalent to an insulator. But when the temperature rises or the light shines strongly, some of the valence electrons on the covalent bond will get enough energy from the outside to break free from the covalent bond and become free electrons. When a free electron detaches from a covalent bond, a corresponding vacancy is left on the covalent bond, which is called a hole. Free electrons and holes are produced at the same time. We call them free electron hole pairs. Then the process of producing free electron hole pairs is intrinsic excitation. The following diagram illustrates the process of intrinsic excitation. It creates holes and free electron pairs. The higher the external energy, the more electron hole pairs will be produced. In the process of free electron movement, it is possible to meet with the hole and fill the hole, making the whole electron pair disappear. This process is called recombination. At a certain temperature, the intrinsic excitation and recombination occurs simultaneously, and when it reaches dynamic equilibrium, the concentration of electron and hole pairs remains constant. We can use the symbol Ni to describe the value of the carrier concentration at a thermal equilibrium. This concentration value can represent either the hole or the free electron, since they have the same concentration. The formula is the one below. However, you don't need to remember it. We are going to look at a set of data in silicon atoms in a silicon crystal at a room temperature. Its thermal equilibrium carrier concentration is 1.5 times 10 to the 10th per cubic centimeter. Germanium is 2.4 times 10 to the 13th power per cubic centimeter. Take copper in the metal, for example. The electron density of copper in the metal is 8.5 times 10 to the 22nd per cubic centimeter. We compare the crystal with the metal. We can see that its conductivity or concentration of conductive particles differ by more than 10 orders of magnitude. So the intrinsic semiconductor is not conductive at room temperature. As we cited before, when pure semiconductors are doped with impurities, their conductivity increases. So we introduced the concept of impurity semiconductor. When you mix a certain amount of impurities into an intrinsic semiconductor, it's called an impurity semiconductor. So it's divided into N-type impurity semiconductor and P-type impurity semiconductor. For the N-type impurity semiconductor is the incorporation of a pentavalent impurity into the intrinsic semiconductor, such as phosphorus or arsenic. For the P-type impurity semiconductor, it is the result of the addition of trivalent elements, such as boron or gallium. Let's look at the N-type impurity semiconductor. In this diagram, the middle atom is an impurity atom with 5 valence electrons in its outer layer. This is a phosphorus atom. Then, 4 of them form 4 covalent bonds with the surrounding atoms. And the extra free electron is easily ionized into a free electron. That is, the impurity atom adds a free electron to the intrinsic semiconductor. As the doping concentration increases, the free electron concentration is much higher than the hole concentration. We call it majority carrier, or major for short. The minority is the holes, and it is minority carrier, impurity element. The 5 valence impurity element is called donor impurity. Now let's look at the P-type impurity semiconductor. The atom in the middle of the diagram is a trivalent element, so when it bonds with the surrounding 4 silicon atoms to form a covalent bond, one of the covalent bonds lacks a free electron, creating a vacancy that we call a hole. That means the impurity atom will add a hole to the intrinsic semiconductor. Well, as the doping concentration of the impurity increases, the concentration of the hole becomes more and more. It is much higher than the concentration of the hole in the intrinsic excited state. In this way, we call it the majority carrier, and the free electron is a minority carrier. Trivalent impurity elements are called acceptor impurities. In impurity semiconductor, majority carrier and minority carrier also reach thermal equilibrium. Respectively, N0 and P0 represent the thermal equilibrium concentrations of free electrons and holes. The product of the two is equal to the square of the intrinsic carrier concentration. It's a formula that holds forever. Let's see, in the N-type impurity semiconductor, the concentration of the majority carrier is N0, which means the concentration of the free electron is N0. We can imagine that as the doping concentration increases, the concentration of free electrons or majority carrier is much higher than the concentration of the intrinsic excited state. So the concentration is approximately equal to the doping concentration, which is indicated by Nd. In the p-type impurity semiconductor, the majority carrier is the hole, and its concentration is represented by P0, which is also approximately the same as the doping concentration, which is represented by Na. There are two conduction mechanisms in semiconductors, which are different from conductors. The two conduction mechanisms, one is drift, the other is diffusion. Let's first look at drift. Drift is a familiar kind of movement or current. That is, the carrier moves directionally under the action of electric field, forming a current, which we call drift current. Look at the graph below. For the semiconductor material, a DC power supply V is applied to it, and under this applied electric field, the holes and the free electrons in the semiconductor do directional movement. The current formed by the movement of the holes is in its direction, and the free electron movement is in this direction. But the current formed by it is also in this direction. So the drift current is the sum of currents formed by the two drift movements, which is the drift current. Now we are going to talk about another kind of movement, which is diffusion. So what is diffusion? It is a characteristic motion in semiconductors. Let's look at the graph below. Let's assume that we have an N-type silicon wafer. We add some light to one of its locations. So let's assume that the right dotted line is an interface. On the left and right of the right dotted interface, its carrier concentration will be different. The carrier concentration here is getting higher and higher under the illumination of light. The concentration is higher and higher. And here, the carrier concentration is lower. The carrier, under the action of the concentration difference, will do a directional movement. The current formed by the directional movement, we call it the diffusion current. In the case of carrier concentration difference, the diffusion current is the current formed by the carrier's directional movement, which is unique in semiconductors. Thus, the total current in a semiconductor is equal to the sum of the drift current and the diffusion current. Okay, this is what we have introduced, the basic knowledge of semiconductor physics. Thank you. That's all for this lesson.